Yeah, so thanks for attending, everybody. We're going to talk about optimizing Julia code today. Yeah, so today we only have an hour, so we're really just going to scratch the surface, give some ideas of what one can do. If you want to read more, these are some nice references. The performance tips section in the Julia manual is kind of essential reading. They're good tips. Follow them when you can, as are these other two references, and hopefully my notes as well. Right, so here's a kind of an overview of how I think about making code faster. If you have code that's too slow, there's some basic things that you should almost always do that aren't necessarily like too costly in terms of the readability of the code or the maintenance of it. And if those basic things aren't kind of good enough for you, then you can start getting into some more detailed optimizations, often guided by a profiler. And we'll talk about some of these stuff in more detail, although we won't talk about parallelization at all today. Right, so the basics here. One kind of standard disclaimer when talking about code optimization is you don't want to optimize too soon. Having code that's complete and correct is like way more important than spending all your time in micro optimizations and never finishing or making mistakes. Also, maybe just as important, you want your code to be clear, readable, maintainable. And some optimizations will hurt those things, make it harder to understand what you're doing. Occasionally they might be worthwhile, but that's a trade-off to be aware of. Yeah, and like I kind of alluded to already, there are some things that you can do that there's not much of a trade-off. They make your code faster, but they also make it kind of clearer and better in other ways. A basic Julia thing is the way it gets good performance is by compiling its functions as you call them. So if you want good performance, your code has to be in a function. This is a pretty one of the first things you might encounter when you're learning Julia, so I won't delve into it too much, but worth mentioning. The other kind of basic thing you can do to get efficient code out of Julia is ensure that your code is type stable. And what this means is that when the compiler sees your function call, it can infer the type of every variable involved, right? If you just read the function's text and you know the type of its arguments, you should be able to determine the type of its output and any intermediate value as well. Doing that enables the compiler to do a bunch of nice optimizations and such. If it can't figure out the types of its outputs, then it has to be way more conservative and it can really slow things down. Sometimes type stability can be somewhat subtle to diagnose or see whether it's going to happen or not. Here's a simple example. Wrote a little function. It takes two arguments. X is supposed to be some kind of array so that we can iterate over it. And then T is some, I don't know, threshold number. And then it's going to compute the sum of the elements of X that are smaller than T. And when X is bigger than T, it's just going to add T. Right, so pretty simple, a very short function. But it can possibly run into a problem depending on the types of the arguments that you call it with. So here I'm creating X as a vector of floating point numbers, 1,000 floating point numbers. And then in this first example here, I'm calling it with a T that's also a floating point number. And And then I'm benchmarking that to see how long it takes to execute. So this at benchmark macro is going to run the code many times and record some stats about how long it took, the range of times, the median and the mean. And so with two floats, it takes, I don't know, 8 microseconds. If we make x an integer and also make the threshold an integer, this 0 becomes an integer, 0 with a decimal point becomes a floating point number, then we get something a bit faster. It's just faster to add integers than it is to add floating point numbers, and it takes 2.5 microseconds. Where we might run into trouble, kind of unintentionally, is if x was an integer and this threshold is a floating point number. Now we get quite a big slowdown. Now it's taking 30 times longer than when we had 2 integers, 6 times longer when we had two floats. So what's going on here? If we look at this function again, inside this sum, it's kind of running through this loop and incrementing the sum as it goes. And initially, this sum will be the type of xi. Say, if say on the first iteration, xi was less than t, then the output of the sum will be the type of xi. Now, if eventually xi is greater than t, then it's adding t to this sum, and now xi is going to be the type that results from, or the output of the sum is going to be the result of the type that comes from adding the type of xi to the type of t. Which, if xi was a float, the result of the sum, or if xi was an int rather, sorry, the result of the sum would initially be an int, but then if t is a float, when we add a float to an int, we get a float. And now the result of the sum switches to being a float. So depending on the values of the arguments, the output of the function can be an integer or a float. And that's what's causing this big slowdown. We can kind of verify that is what's happening by using some of the introspection capabilities of Julia. Specifically, there's this @code warn type macro, which we give it a function call, and then it's going to print some information about what the compiler's learning about the types of stuff. And here, when we give it a vector of ints and an integer for the threshold here, we can see that within here, every variable has a concrete type, right? This 13 thing, which I think is going to be the result of the sum, it knows it has to be an integer because it's always adding ints together. In contrast, if we call @code warn type when we pass this thing an integer and a float, we see, right, what do we see? We see somewhere, instead of body being an int, we see it's a union type, meaning it might be a float, it might be an int, depending on the values of the function's arguments. And if we were actually running this @code warn type in the Julia REPL, it would have some nice highlighting where this union would show up in red, so we could spot it more quickly. Somehow I couldn't get the highlighting to carry through to my slides. Right. Just show it quickly. Run my code here. Right. Okay. So not in red in this highlighting I have, but in yellow it gets bolded. Right. So that's an indication of a type stability problem when you see something like that. So that example was like kind of small and contrived. Here's a more involved example um, from some code I wrote partly for teaching and partly for some research. Um, it's computing some kind of statistic for a generalized method of moments problem. I guess the exact details aren't super important. But on the left, we have a version of the code that introduces a type instability. The root of the type instability comes from this for diff.jacobian call. Because of the way Julia specializes on functions, when you have a function as the argument to another function, this for diff.jacobian isn't able to infer the output type of the function it's being passed. And because of that, the type of GI isn't known to the compiler. And if we look at the output of code warn type down here, you'll see somewhere that, yeah, GI is not just a union type, but it's a any type. It just has no idea what that might be, and so it has to be very conservative about how it operates on GI later on. We can fix this. One way to fix it, at least, is instead of calling the kind of, I don't know, out of place version of Jacobian, call the in place version, where we pre-allocate GI. Now, this GI is definitely going to be an array of floats, and this in place Jacobian will error if our little GI function doesn't return the expected array of floats. And if we browse through the output of code warn type, we would see that there's no instability anymore. GI is known to be an array of floats. In terms of like how much that actually matters, we can do some benchmarking. And here, the difference in speed is about a factor of 5. Yeah. We also somehow reduced our memory usage and our allocations. That's partly contributing to this increasing in speed. Yeah, so we get a big gain from this relatively small looking change to our code that really doesn't hurt it. It just makes it nicer to read, possibly. So it's almost always worth ensuring this type stability is going on. One thing that's kind of a good practice whenever you start optimizing code is to keep around your initial version of a function. And then as you try to create a faster version, test that you're getting the same results. Right? So I inserted that here to verify that the original version of the function and the modified one give the same thing. Because as we optimize, we don't want to lose our correctness, of course. I guess another thing in this, before we move on to more targeted optimization, another thing in this basics bucket of just good things to always do is to ensure that you're using a good algorithm. That's more of a kind of application specific sort of observation. So I don't have a nice example of it, but yeah, you want to compute things in as little steps as possible if you can. Anyways, on to more targeted optimizations. Let's say we've met these basic requirements and we still want our code to be faster. Well, there's a whole bunch of things we can do, but because there's so many options to try, we'd like to kind of focus our efforts somewhere, and the profiler can really help us with that. So what the profiler does is it's going to run some code, and as that code runs, it'll keep track of kind of what line of code is being executed every certain amount of time, every whatever that is, seconds or something. And then at the end, it can print out a nice summary of like how much time each function you called was taking and so on. Somehow I've managed to have that summary not show up here, but that's okay. I thought I had fixed that, but we can see the similar outputs showing up correctly here. And so it looks a little weird out here. This root is just like everything was happening in some kind of baseline Julia process or whatever. And part of the profiling, it was like doing nothing. But then over here is where it was doing something. It's all kind of squished, but we can click on a part to zoom in and see. So there's some stuff from this being like run in the REPL and so on. That's not our code necessarily. And then here it's evaluating the thing that we passed it, this sum. Oh, this is different code than the one I wanted to profile, sorry. Oh, well, that's okay. We can use this as an example. Yeah, here it's evaluating whatever we put in front of the @profile macro, this sum of calling this function a bunch of times in a row. We call it a bunch of times in a row just because if the function doesn't execute for enough time, the profile won't connect enough information to have anything useful to act on. So this function's quite fast, so we're calling it 1,000 times instead of just once. Now this eval thing is in red because it has this runtime dispatch flag. That's an indication that there may be a type stability. That means the compiler didn't know what to do until it was executing the code and saw the values of the arguments. This particular one's no big deal. It's just the nature of having code directly entered in front of the @profile macro. Right, and now here's a bunch of calls to various stuff related to the sum and the fact that we have like a comprehension inside the sum. And then finally, more stuff related to the sum. Finally, stuff related to the actual function we're calling share. Right, so it tells us that a bunch of times we called the share function. Within the share function, almost all those times we were inside this integration function, which calls sum, which calls MapReduce, and so on. And then within the sum used to compute some integral, it's calling this little function share new, which in turn calls some multiplications. And yeah, and some array allocations. The other coloring that happens here are things in orange or whatever. That means there's some garbage collection going on, which what is an indication that you may be spending a lot of time allocating and deallocating memory, which is some idea of a thing you might want to change. If you see a lot of garbage collection, try to use memory in a more persistent way, perhaps. Anyways, if we were working on this example, we would say, well, I guess a lot of our time is being spent on inside this function on this multiplication. Yeah, on line 9 of this source file. So we should think about, can we make whatever line 9 of this source file is doing, can we make that a lot faster? And that's where we would focus our efforts. Now, returning to the example in the slides, which unfortunately was profiling a slightly different function than what was working on the website there. It was for profiling this KLM stable function. What we would have seen there is that a lot of time was being spent in creating arrays and in garbage collecting them and so on. So a reasonable thing to try to do would be to let's create less arrays. And if we look at the source code for this function again, one thing that you might notice is it has all this array indexing with colons. Now, when you create slices of arrays like this, it in fact takes the contents of that you're indexing into and creates a copy of them, and then computes with that copy, which can be quite costly. So to avoid copying, to just like look at the existing array and use those values directly, we can use this @views macro to say to do that instead of creating copies of these slices. So here's a version of the same function that mostly does that. So just put @views in front of there. Additionally, it's now using the broadcasting version of addition and subtraction here instead of the array version. Those will happen in place without creating new arrays to hold the results. So that can also cause a gain. Yeah, and @views down here. When we have slices on just the left-hand side, like this line, we could put @views in front of it, but that doesn't make a difference. When something's on the left, you're operating on the existing array anyways. It wouldn't make sense to like do this division in a copy, right? It would do the division in a copy and then throw away the copy, so that wouldn't be helpful. So this is already kind of using views implicitly, I guess. Anyways, that's the main change happening here. And now we can benchmark this code again. One of the things our benchmark reports that we kind of didn't focus on too much before is a estimate of how much memory is being allocated and how often it was allocated. In addition, let's remember that our median time is 77 microseconds, okay, allocations of 118 kilobytes. We can compare that with the previous version here, where allocations are 173 kilobytes, so a bit higher, not hugely higher, and the timing is 113 microseconds, so a bit slower. We saved about 50 microseconds, 50, 40 microseconds. So other useful ways of reducing allocations can be to pre-allocate and reuse an array as your computation proceeds. Many Julia functions come with both an out of place and an in-place version. An in-place version for putting the results into a pre-allocated array. An out of place version creates a new array. When writing performance critical code with arrays, it often makes sense to use in-place versions and pre-allocated arrays. I don't have an example of that, but that's a common pattern and important technique. The best case with allocations is to eliminate dynamic allocations altogether by using types whose sizes are known at compile time. Um, in particular, the static arrays package gives you something like this. So here's an example of a function that operates on some arrays. And by changing the types of arrays that we pass to the function from the usual Julia arrays, which are what are called heap allocated, the memory is allocated to them kind of at runtime, to static arrays, which get allocated at compile time, call them stack allocated. That name comes from the way so each time you call a function, associated with that function will be a bunch of memory to hold the function's various local variables. And if the function knows the size of those variables at compile time, then the stack will include those like compile time size known variables. And when the compiler knows like the size of those variables, it can do all kinds of nice optimizations. It can like reuse bits of memory when it knows that like it doesn't need that variable anymore. It can put the variables in kind of nice locations so that it can access them quickly. So this can really help with performance. In addition, it's going to just avoid garbage collection altogether and so on. All right, so here we just create some arguments to this function. Here they're heap allocated arrays. Our benchmarks are cut off. Oh yeah, right, we can close that. And then benchmark it, and it takes 70 microseconds. It allocates quite a bit. If we do static arrays, so the important thing is that the size of the static arrays are known to the compiler. So the size of this vector delta is encoded as a parameter to the type S vector of J. Same thing with this matrix and so on. And then because of that, all these arrays live at the stack. There's no need to allocate any memory, and now the function is way, way faster. We in fact get one allocation. I believe that's just to hold the output of the function, because that has to be returned to the REPL. That's the one allocation happening. I guess one remark worth making here is if one, I guess a few remarks worth making. So the size of the stack, I think, is possibly limited, or at least the gains from having things allocated in the stack start to disappear when the stack gets too big. Exactly what too big is, I'm not sure. Possibly depends on the CPU you have and such. So the gains from like following this static arrays strategy are going to be the largest when your arrays are relatively small, say order of hundreds of elements versus millions or whatever. So that's one disclaimer. A second one is if you think you might want to use static arrays, kind of the way you would write code is quite different, or a bit different from how you would write your code if you know you're going to use dynamically allocated arrays. Right? If you know you're going to use heap allocated arrays, then you want to pre-allocate them and operate in place. On the other hand, if you know you're going to use stack allocated arrays, then you don't need to pre-allocate them, and you don't want to operate in place. You want to kind of operate on the whole array at once, the way this code is written. Yeah. Switching between like kind of one style or the other isn't a huge deal, but it's possibly something to keep in mind before you write too many functions that you then have to change later. So there are some other kind of important memory considerations that I didn't construct examples for, but they can be useful for doing optimizations, and they're worth mentioning here. So for various reasons that I guess maybe we'll hint at in a little bit, things will be faster when you operate on contiguous chunks of memory. So Julia stores arrays in column major order. So if you're looping over elements of a multidimensional array, you want your tightest loop to be over the column elements, so that you access elements of the array in the same order that they're stored in memory. And part of why this makes a difference is the kind of various variables and data that you're computing with. It's going to exist in your RAM, your kind of main memory. And then when it's needed, or hopefully just before it's needed, it's going to be fetched into some memory that's local to the CPU called cache. And that moving from RAM to cache is somewhat slow. And then from the local CPU memory, the cache, when it actually needs to do something with it, it gets moved into something called registers, and then in the registers is where like additions and multiplications and so on happen. Yeah, so RAM to cache is much slower than cache to CPU. So one implication of this is sometimes it can help to make your code small so that you have like a function whose stack fully fits on cache, and then it's going to be like faster than if it has to fetch stuff from RAM. So that's sometimes a kind of optimization strategy you might want to try. Another like important consideration is the CPU will try to predict which memory you need before it has to do something with it. So this is called prefetching. It's going to predict what memory you're likely to operate on next from RAM and move it into cache, so it's already in cache when it's needed. Of course, it's not going to be able to predict perfectly, so sometimes it'll need some value that's not in cache, but it then has to go get it from RAM. And this is like costly because it's going to wait a bunch of cycles for the memory to move from RAM to cache, where it can't do anything but wait. So writing your code in certain ways can help avoid these cache misses. Basically, you don't want a bunch of if and else statements inside a loop with lots of numeric computations that's taking some time, because if else statements might cause cache misses. It'll mess with this prediction. You also don't want random memory access patterns. You want to access contiguous chunks of memory, because that's sort of what the cache prediction is going to be best at figuring out. Are there any questions? Oh, there's some. Oh, I see.
I have a question. So if you have a heap allocated array defined inside a function, wouldn't it perform fast because it's inside a function, so it should be JIT compiled and everything should be known at compile time?
So the size of the array is not necessarily known at compile time. In fact, it just inherently is not, because the things the compiler knows when it's compiling are the types of all the variables involved. And so the type of a vector is just vector. It doesn't have a size attached to it. Often, as we're writing our code, we can make the size known at compile time, but then we have to tell the compiler that somehow. So that's where the static arrays come in. Right, so what? So let's say you're optimizing your code profiling it, benchmarking repeatedly, and you've got your memory layout pretty good and your allocation's quite low, and it's still not fast enough. What else can you do? Well, one of the, I don't know, costly in terms of effort and readability optimizations you can do is start using what are called single instruction, multiple data CPU instructions, I guess. So CPUs can do the same operation on multiple numbers at the same time. Current CPUs have registers that hold 512 bits, so they can do 8 floating point additions or multiplications or whatever at once. There's still CPUs with 256-bit registers in use. The workstation that I wrote these slides on, in fact, has 256-bit registers. Anyways, you can operate on 4 or 8 floats at once, no problem. So if you could always use these kind of commands, you can potentially make your code 4 or 8 times faster. Now the compiler is going to try to use these types of instructions when possible. And sometimes it can be successful, sometimes not. For it to work, you need to have your code meet some conditions. You need a loop of fixed length. It doesn't have to be like a known at compile time length. It has to be a loop of fixed length at runtime. So it can't like exit early due to an if statement, like no break or continue. It can't be like a while loop. It also shouldn't have any branching, shouldn't have if-else statements within it. And you need to be willing to reorder the operations, right? Conceptually, arithmetic with real numbers, addition, multiplication, the order doesn't matter, right? With floating point numbers, the order actually can matter. The order in which you do floating point operations changes how you do rounding. So the value of a sum will change slightly as you change the order that you compute the sum. Usually we don't care about that round off order, although sometimes we might. So when we want to say we don't care, we can put an @SIMD macro in front of a loop, and that'll give the compiler permission to reorder the operations in that loop. So to just see an example of how this works with the compiler, here's a function to compute a dot product. So create something to hold the result of an appropriate type. And then just add AI times BI to it and return it. So importantly, in front of this for loop, we didn't put a @SIMD macro. So the Julia compiler isn't gonna try to reorder that loop. It's gonna say, oh, maybe you really care that this happens in orders in sequential order, so I'm not gonna mess with it. And it won't use these SIMD instructions. We can see whether these vectorized instructions are being used by inspecting the LLVM code that Julia is generating, or the assembly code if we prefer. Some people find assembly easier, some people find LLVM IR, intermediate representation, nicer. Doesn't really matter. Anyways, here's the LLVM intermediate representation. There's various comments telling us like which line of Julia code generated this LLVM commands. And what we see, we're getting the elements of our arrays, we're loading them into registers perhaps. Yeah, I don't know exactly. Maybe here we're actually getting the elements of the arrays and loading them into registers and so on. And then here we're calling add and multiply. And so on. And I guess here is our floating point multiply and our floating point add. Right, so the fact that it says fmul and fadd as opposed to something else that we'll see in a moment, as opposed to vmul and vadd, tells us that these are not getting vectorized. It's adding and multiplying doubles one at a time. So for comparison, here's the same function with @SIMD in front of the loop. And now we can look at the intermediate representation and scan through it until we see things like this 4x double. So that means it's doing something where it's loading 4 doubles together into the register. So it's doing some kind of multiple data instruction here. Yeah. In this case, it's initializing, I guess, the values that it's going to store the sum into. And then we see more of these loading 4x doubles. So instead of loading 1 double at a time into a register, we're loading blocks of 4 of them. This loading a block of 4 doubles is like another reason why it's useful to have the thing you're operating on be a contiguous block of memory, right? Because then it can just load the 4 all together. It doesn't have to go look up 4 different addresses to get them. And then we see fmul and fadd being called with these 4x things or something. Actually, I'm not quite sure what those commands mean. Anyways, we see these 4x doubles, and that's how we know that it's doing some SIMD related thing. I thought it was vmul and vadd. I guess it shows up as fadd. Right, so this @SIMD here was successful in doing something. I guess the next thing to wonder is, does it make a difference? And here, indeed, it does. Quite a big difference, actually. Now it's a little puzzling in that I know the workstation that I ran this on has 256-bit registers, so they can only hold 4 doubles at once. And we saw the code was working with 4 doubles at once. So we would kind of expect a 4x speed up, but it has an 8x speed up. So possibly there's some other optimization happening here. But anyways, it's quite a nice performance bump. And it also wasn't at all hard to change the code to get this 8x speed up. Unfortunately, life is not always so simple. This @SIMD macro, it's fairly conservative and limited in what bits of codes it's going to auto vectorize. Now there is a nice package, loop vectorization, that has a more aggressive auto vectorization macro that really gets great performance for all kinds of things. Unfortunately, the creator of the package has decided to step down from maintaining it. And unless somebody else comes forward to take care of it, the package is going to break with the next Julia version. Because it's doing such low-level things, it interacts with the Julia compiler in various ways. So non-public facing compiler internals change with Julia versions, and it breaks loop vectorization. Hopefully someone will come forward and update it, but so far it doesn't look great. One can manually write SIMD code. We'll see some examples of that, but this starts to be more time consuming and makes your code harder to maintain, I would say. Harder to read, at least. Right, so here's another example of just a comparison of some loop that at SIMD does not vectorize, but this at turbo does vectorize. So we could look through the LLVM code and see the difference. But given the time, maybe let's not look at that too much. You just look at the benchmarking. So we see quite a, well, a little bit better than a factor of 2 performance gain from turbo compared to SIMD. So this at turbo is quite nice. Hopefully someone will maintain loop vectorization. However, because one, the days of this loop vectorization package might be limited, and two, there exists code that you can manually write SIMD instructions, but this at turbo macro cannot do it automatically. Maybe it's worthwhile knowing a little bit about how to manually write SIMD code. So here's a version of the same function, but with manual SIMD instructions. So this comes from the simd.jl package, which defines these, well, it at least defines this vec range type. This vec end float might be a base Julia thing. Anyways, it defines various SIMD related things to help write SIMD code in Julia. So we have the same function supposed to be doing the same thing. It has the same first 3 arguments. It adds this additional argument width, which is just the width of the register in floating point 64-bit numbers. So it defaults to 512-bit registers. And now it creates this vec range of n, which is going to be which is useful for taking an array and picking out, in this case, eight elements of that array and trying to load them into a register. And then these vec and float 64s are just things that already exist as that like 4 or 8x double type of thing that we saw in the LLVM code before. And they're just constant values here. They're not going to change throughout our loop. Or actually, maybe TV will get incremented. And then the original code had a loop t from 1 to length of e. Here, we're going to operate on 8 elements of e at once. So we're going to increment t by steps of 8. And each time, we're going to index into t plus lane of e. So this is going to pick out the 8 elements of e, starting with the tth one. Similar idea with this y in. It's going to pick out 8 elements of y, starting with the t plus first one. So it's going to, and then this mul add command is going to do these multiplication and addition of 8 elements of theta 2, TV, and Y at once. Same idea here. And then the way the code works, this TV is supposed to be the value of T, but since we want 8 of them at once, we initial TV to be the numbers 1 to n, and then each time add n to it, so it's getting incremented kind of properly. And then the length of E might not be a multiple of our register width. So when we finish this loop, we've done it in blocks of 8s, we might have a few left over to do. Then this is finishing up those leftover elements just in a single instruction, single data kind of loop. Yeah, and then we can run that code and see here the benchmark is pretty much the same as what the @turbo macro did. I guess slightly faster in this case, though that might just be variation. No, it's probably not variation from run to run. Slightly faster in this case, although that's not typical. Typically, if @turbo has successfully SIMD'd something, it's not worth your time to try to beat its performance. Maybe in some exceptional case, or maybe if you're some expert at CPU instructions, you could beat it. But for the average person like me, it's not worth trying to beat @turbo. But with the future package deprecation, well, I guess we'll have to do things like this if we want that kind of performance.
Paul, I have a question.
Yeah. Mm-hmm.
Can you use SIMD techniques on GPUs?
Yeah, so the underlying principles are very similar. GPUs, instead of having registers that hold 8 floats, they have like kind of the equivalent of a register that holds like 1,000 floats, or maybe more.
But of course the principle is equivalent, but would the code be fundamentally different? And would you have to use different packages, or could you use the same package and similar code? Was my question.
Yeah, unfortunately, it's different packages, as far as I know.
Okay.
One could imagine trying to write a package that abstracts and works for both, but there's nothing out there that I know of.
Okay, yeah, because VMAP in JAX does exactly, it does SIMD vectorization, and it does work on any device that runs, that the XLA uses. So JAX has exactly the same code that can work everywhere. So that's why I was wondering. Okay, thanks.
Mm-hmm. Yeah, maybe there is that I just don't know about, but as one further motivation for bothering with manual SIMD code, you can have functions that just loop vectorization can't deal with, and @SIMD doesn't do anything for them, but you can still usefully write manual SIMD code. Just another example. If you're familiar with the regression, this is just computing like x prime x and x prime y in some kind of loop. Yeah, in a loop for some particular regression specification. And with the code written with @inbounds and @SIMD, I believe it fails to do any SIMDing. If you put @turbo here, it crashes. No, maybe it doesn't crash really. It returns an error at least. It doesn't like this sort of thing. But we can still write manual SIMD instructions here. This loop is like, in some sense, easy to parallelize. It's just adding stuff up together. The order doesn't matter, so we can do this sum as blocks of 4 values at once, no problem. Or 8 values or whatever. So that's what I do over here. then again, something to pick up the remainder, and that's it. And then, yeah, we get almost a 4x speedup. Maybe that is a 4x speedup, which is quite good. It means we're kind of, which is what we'd expect from our 4 registers that we have here on the machine that this was running on. So I guess we just have a couple minutes left. So if there's any questions, this was what I wanted to cover. I guess to conclude, maybe let's just open the little outline here. Let's go back to our overview picture. So just to reiterate, kind of following this like basic advice of type stability and using functions, probably always a good idea. Profiling, finding bottlenecks, and then fixing them by thinking about reducing allocations, and maybe switching to static types is usually worth your time and worthwhile. Doing really micro optimization by manually writing SIMT code, that's kind of for special cases. If you enjoy it, that's great. If you're writing code that's going to run for thousands or millions of CPU hours, certainly worthwhile. And that might be the case if you really operate at a large scale or you distribute your software to a lot of users. But for many, I think, workflows, it might not be worth your time necessarily. Still a useful technique to know about and think about.